Okay, I was just looking over a problem with Mira before class, and I was sitting there floundering about, and then in the last 3 minutes, I had the epiphany that during an adiabatic process, pressure times volume raised to the gamma power is constant. And gamma, as we did learn, is the ratio of Cp, the molar specific heat at constant pressure, to Cv, the molar specific heat at constant volume. And so gamma for a monatomic ideal gas is 5/3. Remember, we went through the whole degrees of freedom thing in calculating what the Cp and Cv are. So that will definitely help for that problem. Yeah? Okay. We will finish all thermodynamic stuff today, which is good because we have a test on Tuesday. I will, by Sunday, post on Moodle a series of worksheets for the different chapters. And then I will work as quickly as possible to post on YouTube guiding you through the worksheets as well. So you just don't ignore the emails that come from Moodle, and you'll get updates on when those things are available. Entropy. I ended last class period talking about entropy, and we have these equations. This is, I believe, the only one that our textbook takes advantage of. That if you have a change in a heat flow at constant temperature, that the change in entropy is the heat flow divided by the temperature. The other equations there are all correct equations. The top left one is the most important one in reality because that's the definition of entropy. The number of microstates in a macrostate is that omega parameter, and Boltzmann's constant times natural log of that gives you the entropy. So with my example that I used at the end of class last period, I said if we were to roll dice, 2 dice, macrostate, nice. Number of microstates and the actual microstates. So what are the different outcomes you can get with 2 dice? You count the number of pips showing when you roll the dice. What's the minimum number of pips you can get? 2. And then goes up by 1 to what's your maximum? Yeah, if you have standard 6-sided dice, yes. Okay, so now we have the number of microstates, and then over here I have the microstates where I'm actually going to write them out. So we're starting by saying we have 2 dice. We roll each die can have a number between 1 and 6. So to get 2, the first die will be red, and the second die will be green, and they both have to be 1. So there's only 1 microstate that gives you 2. For 3, I could have or either one of those gives me 3. So that means that there are 2 microstates for 3. And likewise, as you go on, if you get to 7 could have that's 4. I'm doing them one at a time for color. Right, those are all the options to get you 7. And so there's 6 of those. Now, if we want to calculate the entropy, what's the natural log of 1? This is the only natural log that I expect you to actually have memorized. 0. So natural log of 1 is 0, hence your entropy. Remember right here, S is equal to K natural log of omega is 0. For 3, it's going to be K natural log of 2. And you probably do know that's 0.693, but who wants to write 0.693, especially when I don't know any of the others? The next one, K natural log of 3, and so on, till we get down here to K natural log of 6. And then it goes back down to 0 for 12. So we have entropies, and we can calculate the entropy of those rolls. Now, this calculation of entropy probably doesn't match with anyone's pre-existing understanding of entropy. Most people's pre-existing understanding of entropy plays much more along the lines of, let's suppose that I have 10 bricks, and they're all stacked up one on top of the other. How many ways can I have 10 bricks? Let's make it a smaller number. 3 bricks, because we can do that in our head. How many ways can we have 3 bricks stacked one on top of each other? Let's say we number them 1, 2, and 3. We can have 1 on bottom, and then 2 and 3, or 3 and 2. So there's 2 options with 1 on bottom.
I misinterpreted.
We have 2. That's fine. That's fine. We have 2 on bottom, and then there's 2 options. We can have 3 on bottom. There's 2 options. So how many different ways can we stack them and have it? 6 ways. Now, we say, okay, now we have these 3 bricks. Instead of having them all stacked on top of each other, we're going to have them sitting all on the table at the same elevation. How many ways can I have those bricks sitting on the table? I can change the orientations all over the place, right? And it's still equivalent. Now, with the bricks stacked, I could, of course, move the bricks around like this, but there's a whole lot more options of where I can place 3 bricks than where I just placed 1 with the other 2 stacked on top. And so that's why there is more disorder when they fall down, because there's more ways I can arrange those bricks to get the same overall, in this case, potential energy. So that's where we get the idea of disorder for entropy from. It's correct, but it comes down to statistics. Something I often do is talk about the entropy of card hands. You know, you're playing poker. Which hand is going to have the highest entropy? What? Okay, a straight. Let's go with a straight flush. The straight flush, you can get a straight flush a lot of different ways, but it's a pretty limited number still, because you have, there's 14 minus 5. All right, 14 minus 5 is 9 for each color, and so 9 times 4 is 36. There's 36 ways to get a straight flush.
So, is it a pair then?
What was that?
Is it a pair? Because you can get that so many different ways.
Well, a pair has a very low entropy, or excuse me, high entropy. Yes, high entropy, because you can get a pair lots and lots of different ways. I'm not going to try to do the calculation right now because I'd have to stop and think for a minute or so. So when you're doing the hands, on poker players, they know all the odds. They pretty much memorize them. Either that or they're really, really good at math. But they know the odds of these hands, and they know I've got this, the odds of filling the hand or this. And entropy plays a big thing into it, except for one thing. Okay, so the strongest hand you can have at poker is which one? The royal flush. Why would it not be 4 of a kind? Well, with 4 of a kind, there are 14 different 4 of a kinds. That's a lower entropy, isn't it? But four of a kind, well, what's four of a kind? Four of a kind beats everything but a straight flush, right? Straight flush. And yeah, the straight flush, well, yeah, I'm trying to get this all straight. The royal flush is the highest hand, but oh yes, here's why. I forgot, you have 5 cards. There's 14 ways to get four of a kind if you only have 4 cards. But with the 5th card, you have all the rest of the deck to add to the ways you can get it. So that's why the straight flush is the lowest entropy. But what if somebody said, you know, I've got a 2 of hearts and a 7 of clubs, and they name their specific 5 useless cards. They say, what's the entropy of this hand? There's only one way to get exactly that hand. So you have to define what your state is you're looking for, what the macro state is, to really get the entropy right. Right? If you were saying 4 of a kind, that's a different thing than to have this card, this card, this card, this card, this card. There's only one way to get that, has an entropy of 0. If that's how you define your state. Okay, enough on the statistical approach. I do want to mention this picture here, which I believe comes from the textbook, is very useful to understand some things about origins. I am a believer in creation. I don't believe that life, developed through abiogenesis. One of the arguments that other creationists like me will use is that as you develop a more sophisticated system, i.e. you go from a little eukaryote or something into a trilobite, that you have added a lot more order. And so you violate the second law of thermodynamics. How many people have heard that argument? Okay, we have a number of people. There are 2 things that people who make the argument usually miss, and I think one thing people who argued against it miss. So the 2 things that they miss is, well, let's take Ryan. At one point in time, Ryan was just a little zygote. And he's developed a lot from there. Is he a violation of the second law of thermodynamics?
Yes.
No, he's not. We simply would not hold on to a law that's so easily disproven. So how is that possible? Well, the second law of thermodynamics, as stated by Planck, is that every process occurring in nature proceeds in the sense in which the sum of the entropies of all bodies taking part in the process is increased. So while the entropy of Ryan may have decreased, Ryan is constantly doing things. He is taking in energy, exhausting energy. And you have to consider what's happening with the environment along with Ryan. Now that was a fun example just because I can use a person. But it's just as easy to talk about freezing an ice cube. When you go from water 0 degrees to ice at 0 degrees, the molecules are now in fixed positions rather than free to move about. That's just a much grander example of my 3-brick thing. You have a lower entropy in the frozen state because they're in these fixed positions. Instead of free to move about, much higher entropy when they're free to move about can have all kinds of positions. So what happened to the entropy of the ice when you froze it? It goes down. Is that a violation of the second law of thermodynamics? Is that stated by Planck here? No, it's not. Once again, otherwise we wouldn't hold on to it. So how can Planck's statement be true if we most definitely have a decrease in entropy of that ice? The environment had to increase in entropy to make up for it. We're going to do a problem with this in just a moment. Now back to the creationist, evolutionist debate using entropy. The person who supports abiogenesis will say, oh, sure, the entropy of the system may have decreased, but the entropy of the universe increased at the same time, just as when a human develops. And it's a valid argument. But the second law of thermodynamics is really just a statistical statement, like we said before, that the most likely thing is what's going to happen. So here's an example I like to use, that our textbook like to use. You can have all of the molecules in a corner and still have the same, same temperature, pressure, and volume. Or you could have, it's the same volume, it's just supposed to be empty. Or you can have fill space. You could take this room, evacuate all the air, have it seal tight, and then put air in the corner and release it. And as the air goes from being in the corner to spraying out in the room, what's going to happen to the entropy of the gas? Actually, it's going to go up because there's a lot more position for them to have. So the entropy goes up as it fills the room. And according to all laws of physics, they could go back there again. But we all know they're never going to do it. Because it's so improbable, because the entropy of them being back there is so low, the probability of being all back there again is virtually zero. And so nobody ever says that, oh yes, we should worry. We could suffocate in this room because all the air molecules could go to the corner and we have nothing to breathe. No one says that because it doesn't make sense. We know the statistics say that can't happen. Well, if you look at the creation, the abiogenesis requires very unlikely things to occur. And scientists or people who are supporting abiogenesis will say that I've heard people make this argument. Well, we have the ultimate evidence that that's what happened because we exist. That's rather a circular argument. Yeah.
I have a question. So what is the entropy of being inside of a vacuum? Like, is that a high or low entropy?
Okay, if you have a perfect vacuum, then you have an entropy of 0.
Okay, just making sure.
Okay, so back to this. The evolutionary process, the process of developing an organism that's living and breathing, requires constant increase in your, or decrease in your entropy, and increase in the organization. And you can have 1 or 2 steps to do that randomly. But to have it build and keep building and not fall down is really unlikely. You have, Le Chatelier's principle that says that you can basically, this is the way it was explained to me, you can build a sandcastle, but over time it's going to flatten out, right? The same idea, species are generally going to devolve rather than evolve. There's a few more topics on that I could go into, but I think that I need to go on for time's sake. So let's do a problem. Let's first talk about how a refrigerator works and then do a problem with the refrigerator. We probably all have refrigerators. We don't use ice boxes anymore. Ice box, you actually had ice that you would put in there, and that ice would then keep stuff cold. My grandmother always called it an ice box because, well, she was born in 1912. So how does a refrigerator work? A refrigerator is a heat pump. It's going to pump heat the opposite direction that it would naturally flow. And the way we do that is with a fairly simple mechanism. You start with a compressor pump. So you take gas, or it's not gas in this case, it's your Freon, and you compress it. What's going to happen to the temperature of a gas when you compress it? You have PV equals nRT. If the P goes up and V stays the same, then the temperature has to go up, which is what you said, right? Maybe it's behind you. I heard somebody that did. Yeah. So the temperature is going to go up. So you compress this gas, or this Freon, this coolant. I shouldn't even say Freon anymore because Freon is a chlorofluoro or fluorochlorocarbon that causes ozone to be catalyzed in the atmosphere, and it can be broken apart by visible light and thus weakening the ozone layer, and so it's banned now. You can still get a little, but it's really expensive. You can't make a new refrigerator with Freon. Okay, so your refrigerant, you compress it, it gets hot. So this hot refrigerant then goes through coils outside of your refrigerator. And you have air out there, room temperature air. Coils with hot coolant in it, hot refrigerant in it, air out here, the air comes by. You're going to transfer heat from the coils to the air, making the air warmer and cooling the coils. So by the time the refrigerant's gone through the series of coils, it's reached roughly room temperature. If you've ever played around with the back of a refrigerator, yes, you will burn yourself if you touch the part right next to the pump. They don't make that stuff available anymore. You can't just reach there and touch it like when I was a kid. For obvious reasons, safety. So you're going to have basically room temperature refrigerant after you've gone through those coils on the back of the refrigerator. That's why the back of the refrigerator is always going to be hot when it's running, because that's where you're expelling the heat that you're pulling out of the interior of the refrigerator. Then this thing here is not named, but it's super vital. It's an expansion valve. It allows the gas to expand into the low pressure region. As the gas expands, what happens to the temperature? It goes down. So now you have this room temperature refrigerant that is allowed to expand and suddenly cools. I don't know if you guys have done this, but if you take your aerosol can and you shake it all up and turn it upside down for best effect, you spray it on your skin, what happens? Yeah, cold. This is one of those things that idiots do on the internet. I'm going to take the aerosol challenge. And they freeze their skin because they're geniuses. I trust you guys don't do that, right?
Right.
Makes it so, well, now that you mention it, that sounds like a good thing to do. Not as a challenge, but just because I'm an idiot, I've done it. So,
As long as you do.
Yeah, as long as I. So you now have stuff that went from refrigerator temperature to high temperature when you compressed it. Then you cool it down and you let it expand. It's going to go down to a really low temperature. And so that really cold coil then goes inside the refrigerator. And of course, heat naturally flows from hot to cold. So it's colder than what's in the, freezer compartment is what I'm going to talk about here. And so you have heat flow from the freezer compartment into the refrigerant, warming it up. And so it comes out here, like maybe -1 degree Celsius. Brr. That's warm compared to what it was there in the refrigerator or the freezer compartment. And so that's how a refrigerator works. It's just taking a material, a refrigerant, that works pretty well for this process of compressing and it getting hot and letting it decompress and it gets cold and running it through that cycle. So it's not some magic box. Now, doing a real problem. Consider a freezer with an internal temperature of -18 degrees Celsius and a house maintained at 20 degrees Celsius. What is the Carnot coefficient of performance for the freezer? What's special about the Carnot? It's the ideal. It's the best you could achieve. And with the Carnot cycle, remember, coefficient of performance is what you want out. Well, if you have a refrigerator, what is the key thing you're interested in? Are you interested in the heat that you exhaust to the environment or the heat that you remove from the freezer? Heat that you remove. So that's the heat at cold temperature. And then you divide it by the work you put in, which we'll use QH minus QC, because for either a heat engine or a heat pump, you have delta U equals 0 for a cycle, so work is equal to Q hot minus Q cold. And if it's Carnot, that's general. This isn't always true statement for coefficient of performance. For a Carnot cycle, the heats are proportional to temperature, so for Carnot, I replace the Q's with T's. So what's my temperature hot? 293. What's my temperature cold? Yeah, I'm just trusting the man. I don't think I should, though.
Oh, yeah.
I was going to. Now, if you look at this, that's a difference in temperature. It didn't matter if I had it in kelvins or Celsius because we add 273 to both cases. But for the number on top, because it's the actual temperature, it matters. I have to use the 255 kelvins on top. So what do I get when I take 255 divided by what turns out to be 38? So this has a Carnot coefficient of performance of 6.71. What that means is if I put in 1 joule of energy for my work, I'm going to move 6.71 joules of energy out of the freezer. How much energy then will be dumped into the environment? I put in 1 joule into my heat pump. I removed 6.71 joules from the freezer. How much goes to the environment? 7.71 joules of heat is exhausted to the environment. And of course, the underlying calculation we did for that is just this red equation. Work is equal to Q hot minus Q cold. So we have that down. Now, any questions about the coefficient of performance calculation? This is not possible because the Carnot cycle is not possible. This is the ideal. Your real refrigerator is not going to be, 6.71 coefficient performance. It's going to be a lower coefficient performance. But now for some calculations involving entropy. What's the change in entropy of the water when freezing 100 grams of water in the refrigerator or freezer?
Question. So if we can't achieve that with refrigerators, why do we?
Because it's a goal. When you're trying to design your refrigerator, if you are like at 6.68, you're like, I am not going to spend any more time and effort trying to improve the coefficient of performance because I am darn near perfect. Whereas if you're at 1, you're like, I think I could really make this more efficient.
Okay.
That's the goal.
So it's a goal. Okay.
It gives us the target. Now I'm going to do the rest of this problem saying it's running at Carnot efficiency. We know it's not going to be that good. But the first part doesn't matter. What is the change in entropy of the water when freezing 100 grams of water? So first, it's freezing water. Why freezing water? Because freezing water is an isothermal process. The temperature is staying constant. Now, it's not a gas, but it's still the same thermodynamics. It's going to be constant temperature, in which case my change in entropy is given by change in entropy is Q over temperature. I'm going to write that so it doesn't. Now I'm going to come over here to the right and write it again. And you do have this in your homework. I was going to have a student do it, and I was like, well, no, I'll do it. How do I calculate the heat that's necessary to freeze my water? What was it? If I was changing temperature, that would be right. If it's changing temperature, Q is MC delta T. The problem that has this has both parts. It has that part first and then changing phase. If it's changing phase, what is it? Mass times the latent heat of fusion if it's changing between ice and water. It's actually because it's freezing, it's going to be negative because heat's being removed. So that's going to be my mass, and I said 100 grams. Put the minus out front. times the latent heat of fusion, which was 334 joules per gram. I have that written at the bottom of the slide here. 334 joules per gram. And then divide it by what temperature? This is water freezing. What's the temperature? 273 kelvins. 0 Celsius would be correct, but what would you get if you put 0 Celsius into this equation? A division by zero error, undefined. You have to use kelvins. And so if you calculate that, what does it give you? Notice the units are joules per Kelvin for entropy. So we've calculated how much entropy change there was for freezing the ice. It's negative. That's a lower entropy because it's becoming more ordered. Is that shocking? No, that's what we expected. Now, what is the change in entropy of the environment for this process if the freezer runs at the Carnot level? How do I calculate the change in entropy for the environment? This is outside the refrigerator. What's happening outside the refrigerator? I have the Q hot being exhausted, right? And divided by the temperature hot. And so I have to calculate what Q hot is. Well, from our definition of coefficient of performance, I can calculate Q hot. So solving that for Q hot, first thing I'm going to do is put Q hot minus Q cold is equal to Q cold over coefficient of performance. And then I'm just going to add QC to both sides. And I get Q hot is equal to Q cold times 1 plus 1 over the coefficient of performance. So now I can come back here. What was my Q cold? Well, my Q cold was 122.3. Or it's not 122.3. It was 100 grams times 334 joules per gram, or those are threes. Because the Q cold was the heat that was necessary to freeze the ice. We already used it, but we never did the simple calculation. So that was my Q cold. So for my Q hot, I'm going to have 33,400 joules. I did put joules, right? Yeah. Times 1 plus 1 over 6.71, because that's what we just calculated right there. Divided by our temperature hot, which was 293, yeah. And so if we calculate that, what do I get? 130.9. So how did my total entropy change for freezing this ice? What was the change in entropy for the universe? What? Did it go up or down? Up by 8.6. Because we had a drop of 122.3 for the ice and an increase of 130.9 for the exterior. Now, if we're running in a Carnot cycle, if I calculate the change in entropy for the inside of the refrigerator when I have this much heat leave the inside of the refrigerator, or I would have gotten the same 122 point something. The freezer, if you're not heating or cooling anything and it's just kind of maintaining, you would have no change in entropy for the system if it's Carnot. For anything real, you're going to have an increase in entropy for the universe. So that was all my questions on this. One last question that's not stated. You live in your dorm room. You have a refrigerator. The heating and cooling in the dorm is just like in this building, kind of out of whack sometimes. Sometimes it'll be hot in your room. What happens if you open the refrigerator door? Is that going to heat your room or cool your room? Okay, I haven't answered. It will cool it. Let's go back to what we saw with this refrigerator. How much heat is removed from the interior? It was 33,400 joules. How much heat was exhausted? It was... Okay. No, the heat. The heat would be 33,400 times 1 plus 1 over 6.71. So you have 3,800 or 38,000. Okay. 38,377. So you have more heat being exhausted into the room than you're taking out. So what's going to happen to the temperature in the room if you open the refrigerator and leave it open? It's going to go up. The refrigerator is going to heat your room, not cool your room, because the Q high is always larger than the Q, or Q hot is always larger than the Q cold. Now you, being in a dormitory, and don't do this, okay? Refrigerators are heat pumps, but they're optimized for a certain situation and it's not cooling a room. But if you were so inclined, you could take that refrigerator and mount it in the window so that the hot coils are outside. And then you could open the refrigerator door and it would cool your room. But it wouldn't do it very efficiently. Right? A little window unit is doing the same thing, but it's optimized to work in that situation. So the window refrigerator is going, or not refrigerator, the window air conditioner is going to be optimized to do that job, where the refrigerator is not. Question?
Yeah, I'll come clean. Like I tried to get my room cooler when it was hot. Doing that, and yeah, it didn't work.
Now, if you stand right in front of it, you feel cooler right there, but the room is warming up. Now, my wife and I can argue about this forever. I'm a physicist; she's not. She believes that turning on a fan will make a room cooler. No, that's right. Because what is the fan doing?
It's exciting the molecules.
It's making the molecules move faster. If they're moving faster, that means they have a higher temperature. Now, it's not going to heat it very much. But it is net heating. So like when you leave the room, don't leave the fan on. When you're in there, the fan feels good because it's going to cause you to cool down. Because it's enhancing the evaporative cooling. The air flows over your skin, takes away the hot air, replaces it with cool air that will take off more moisture. It feels good. It helps to cool you. But it still has a net heating effect for the room. So when you're out of there, turn it off. We don't need to heat the room and cost money. The same. Of course, I'm really stingy too. We could just turn up the AC and all will probably be solved. All right, that ends it for material that will be covered on the exam next week, or after Thanksgiving. Now we get to move it. Oh, only 10 minutes? Seriously? You guys just spent all this time doing those reading quiz questions. I only got 10 minutes to get into waves. I will have to do some adjustment on the reading quiz schedule from here on out just to get us back into sync. Because we're like, what, a lecture and a half? Let's say a lecture and 5/6 behind. So, yeah, I'll look at that. Simple harmonic motion. Simple harmonic is a special kind of repeating motion. Repeating motion we call oscillatory. Things that oscillate. It's oscillatory for you to come to this class. For most of you, you come to this class 3 times a week from 11 to 12, right? And so that's something that you can consider oscillatory because it just goes back and forth. Now that's not a nice clean repeat because you have, Monday, Tuesday, Wednesday, Thursday, Friday, you had a gap of 2, 2, but then you go Sabbath, Sunday, Monday, you have a gap of 3, so it's gaps of 2, 2, 3. It's not uniform. Well, we like, especially for a general physics class, we don't like that. We want to analyze only things that are uniform, that are repeating of the same frequency. So there's a new word, frequency. Frequency, I think everybody understands this, but I have to say these words to make sure that there's no misconception. Frequency is the rate at which things reoccur. So rate means per unit time. So the frequency is how many occurrences per unit time. So you could say the average frequency for you coming to class is 3 times per week, times per a unit of time, or instances per unit of time. The standard unit for frequency is the number of times it occurs per second, because second is the standard for time. And so we have the name Hertz, that is the unit we call 1 cycle per second. So a Hertz, 1 cycle per second, 1 repeating per second. Now we're further going to restrict ourselves to simple harmonic motion. Simple harmonic is, you can approximate most natural oscillations to simple harmonic. It's only an approximation. As we'll see with the pendulum, it's not correct, but it's an approximation if you have small oscillations. So what is it? Simple harmonic oscillation is the oscillation that occurs when you have a restoring force that's linearly proportional to displacement from equilibrium. 2 important things there. Restoring. Restoring force means if I take the object and I displace it from its natural position. The position, we call it the equilibrium position, the position that it would naturally just sit at if I didn't disturb it. If I take it away from there, that's what the x in the equation there is. It's the displacement from equilibrium. Then there's going to be a force. The minus sign means the force is in the opposite direction that I displaced it, restoring, bringing it back. And then kx means that it's linearly proportional to how much I displaced it. K is just a constant for proportionality. This equation should look familiar because this equation is Hooke's law. That's the equation for the net force in a spring. So the easiest simple harmonic oscillator I can make is having a spring with a mass on it. So notice the spring's length is here. Whatever, I'm not measuring it. If I put the mass on it, it goes from here to here, stretch that much. Where is the equilibrium position for this system? It's not, because this system includes the mass. If I didn't have this mass, it would have been there. That's kind of an important thing to keep in mind. So this is the equilibrium position here. And so if I displace it, if I pull it down, there's a net force pulling it up. If I raise it, there's a net force bringing it down. And that net force is proportional to how much I displaced it from equilibrium. Now, in this case, there is a constant downward gravitational force, and it's easier to understand if you do it horizontally, then you don't have to worry about gravitational force. But you have 2 important aspects here, the minus sign and the linearity. Minus sign means it's restoring it toward the equilibrium position. Linear with x. Now I said most systems can be approximated like this. For small deviations, and I just happen to know that 2 of you, because Michael's not here, have been studying this in calculus recently, that you can take any old function and you can make a Taylor expansion or Maclaurin expansion, I don't remember which one's which, but the one that's expanding about the equilibrium position. And the first term is going to be a constant. Then the second term is a linear term. And so if we can do that with any complicated function, then if it has small oscillations, it's going to behave linearly. Large oscillations, not so much. So it occurs very regularly in nature because of that. What are the two things that your net force must have if you're going to have a simple harmonic oscillator? This is super important. What are those two things? Two of those are correct answers. Actually, I probably have. Okay, Ryan says A and B, the force must be constant. No. No. B, the force must be linearly proportional to displacement. Yes.
A.
That's in direct opposition to A. You couldn't have both of those two at the same time. So it has to be linearly proportional to displacement. What was the other one? Okay, I heard is at F. Net force must be in the same direction as displacement. It's the opposite of F, which is G. The net force must be in the opposite direction from displacement. It has to be a restoring force, something to bring it back to equilibrium. I have 1 minute left. Energy. You had lots of questions with energy, and I apologize. Those reading quiz questions some of them were just way too hard. I mean, they're like total homework problems.
Yeah.
The goal of a reading quiz is supposed to be you read it. Hey, look, there's the answer, and you write it down. That's the goal. And yeah, I looked at it, I'm like, that's a problem. You actually have to sit down and calculate it. Now, if they had an example and you're just saying, oh, here's the example and there's the answer, that's fine for reading. So I apologize. I used to write my own, and maybe it would make more sense. I mean, there's educational pedagogy involved here that is the latest research. It does things like the spaced questions where you're asked questions of things you studied a month in the past or something, or a couple weeks in the past. That's supposed to help you so you remember it, so when you get to the final, it's still there in your head. But yeah, I wasn't happy with those questions. For a spring, we already did this graph, and we learned that for a spring, the potential energy for a spring is equal to 1/2 K times the amount stretched squared, which this was calculating the work. The work you put into is how much energy it stores. That's an important factor. Remember when we had the pendulum and I had the bowling ball up to my chin? What kind of energy did it have when it was at my chin? Potential. When I let go, what happened? It converted it from potential into kinetic, got to its lowest point, which would be its equilibrium point, because if I stop the ball, that's where it would be. And then it converted it back into potential energy. Well, that's what a simple harmonic oscillator actually does. It's converting energy back and forth. And so if we're going to work with the spring, we'll talk about the potential energy in the spring and the kinetic energy. Okay, I'm out of time. Have a great Thanksgiving. Thank you, Nate.
That one was exciting because I'm so frustrated.